the
Hello.
amazing Eli Silver.
Yay.
Hi. Lovely to see you both again. It's been not too long, but longer than I'd like.
Yeah.
How has the stream been so far?
It's been great.
It's been amazing.
We've been having a great time.
Yeah.
Incredible.
We're hitting
So
about fluids.
Tell us more.
yeah, so today I'm going to be showing off a couple of the projects that we've maybe featured in past Harris Lab open hardware expositions, but there's been progress on all of them. So hopefully it'll be some new stuff and some cool demos. We love the live demos. So a little bit about me. I'm Eli Silver. I'm a research engineer at the Harris Labs. So that's a title that we are constantly deciding what it means day to day. But basically, I design a lot of the experimental equipment and keep the current experiments running for our lab. And because of my interest in open source hardware and open science, as well as Dan Harris, who's the professor who runs the lab, we have the privilege of developing tools for ourselves that, if they seem like they'll be useful to other people, other researchers, other experimenters around the world, then we try to put in that extra time and effort to document things well, to design things in a way that's replicable by other people, and then to release it as open source, hopefully certified, and yeah, put that out into the world. So at Harris Labs, we do, maybe I'll start with a tour. That's fun. We do a variety of experiments that all involve fluids in some way. So this is a vibrating bath that we use, and we can fill these discs with fluid, usually water or water plus some glycerin to change the viscosity. And then we can place objects on the bath, and when we oscillate it, we look at it with a camera up on the ceiling, and we can study how these objects move in response to this oscillating forcing, or even how collections of them interact with each other. We do a lot of experiments with droplets. So this is our most kind of sciencey looking experiment, which is this is a vacuum chamber. And inside of the vacuum chamber, if I can turn on the light, there is another open source project from our lab called the droplet generator. So maybe I'll show one that's not in a vacuum chamber in a minute, but this guy up here is a droplet generator. It uses a piezo actuated disc that flexes, and there's a trapped volume of fluid with a little nozzle at the bottom. And every time the disc flexes, or we put in this like square wave pulse, it shoots out a droplet. And what we're experimenting with in this, or what we're investigating with this new experiment, is what happens to the droplet when it hits something. So often they'll bounce, and the bounce happens because as the droplet's falling, it's compressing the gas between the droplet and some like fluid film in this case, or some liquid bath. So what happens if you remove the gas, or what happens if you remove some of the gas, or what happens if you replace the gas with, in our case, CO2 or helium or a different gas that might change the dynamics. And so this is kind of a new, no one's done these experiments under different atmospheres quite like this with this much control, so that's been really exciting. And this is like the droplet generator, which is this tool that other labs can go on our GitHub.com/harrislab-brown/dropgen and build their own. And then we're applying it to this new context, which is different atmospheres. So here's an example of a drop generator that's maybe a bit easier to see. So we put different substrates down here that we want to bounce droplets off of. And then this is the head. And it has a nice little M6 3D printer nozzle from like an Ender printer or something right there. And inside is a piezo disc. And this whole thing will get filled with fluid, either water or oil. And then at the back, there's a reservoir. And the reservoir is aligned so that it's the same height as this, and we kind of can fill the whole thing up. And if this is a little too high, it'll kind of siphon fluid out and drops will start dripping, which is we don't want. And if it's too low, it'll siphon back that way and suck in air through the nozzle. So we've got some like adjustment built in here with a flexure. And yeah, so this allows us to do really precise droplets on command, different sizes. And we can change out the nozzle and you can 3D print your own. So that's kind of like a tool that we think could be useful to not just us, but lots of people. Here's an example of a tool that I've been working on for a few months, along with some other researchers in the lab, that is maybe another kind of like built in the same style, but not necessarily useful to other experimenters. So this experiment, we have this ring right here, and we place it on the surface of the water and we shake it. And that makes these nice little waves. And then we have this big linear actuator that goes way up to the ceiling, about 6 feet in the air, or around 2 meters. And at the end, we have a solenoid that is just a like magnet wire wrapped around a 3D printed coil, or a 3D printed mandrel. And then we can drop little steel ball bearings that have been coated in a special hydrophobic coating. We can drop them into the waves. And by using some code that we wrote running on a microcontroller that controls both the motors and the solenoid and knows about the height of the system, we can actually time it so that that droplet impacts the water at a certain phase. So at exactly, when the wave's at a peak or at a trough or somewhere in the middle. And so this is allowing us to see how the air entrainment behind the ball, the splash that comes off of these impacting spheres changes with the wave phase. And so far we haven't found anyone else that's been able to, that's built a system that can sweep through phase angle like this. And then the whole thing gets filmed by 2 high-speed cameras, one for the splash and then one for the air entrained cavity. And this is kind of a lot of our experiments are do something and film it and then process the data later. So that's an example of something that's maybe built with the same sort of 3D printer, and it's literally just a hacked Delta printer that I found in like a makerspace parts bin with some custom electronics, but it's pretty specific to our lab, so that might not, maybe if other people are interested, we could do the open source treatment on it, but for right now, it's kind of just a project for our lab. We have this wonderful makerspace, which has laser cutter, 3D printer, some resin printers, hand tools and stuff like that. So a lot of the experiments and experimental setups we're able to just build in the lab. Remember seeing this CGI? So yeah, can anyone hear me okay? Is that good? So yeah, our lab is the lab that does the multicolored lighting, and we care a lot about the aesthetics of the science, and we think that can kind of bring a lot of people into the fold of fluid mechanics, make it more interesting. Here's an example, a poster on the wall that won like a award at a fluid mechanics conference. So this is one of our experiments showing fluid structure interactions. So in this case, we have a big tube with a ball on the end, and then the ball is connected to the tube by a spring. And so by changing the spring, we can change how the structure oscillates during the impact. So it's this two-way coupling between the water and the structure, and then the structure back to the water. And so you can see through the different kind of frequencies of undulation, from rigid, more stiff, less stiff, even less stiff, how it changes the impact dynamics. Measure all that with things like accelerometers, and again with some cameras. Okay. What did I do? Oh god, oh no, everything's broken. All right. How am I doing on time? Pretty good. So, if I can figure out how to share screen. Share screen. Oh, that's annoying. So unfortunately, it won't let me share screen without restarting the chat. So I'm not going to do that. The restarting the page. So okay, so this is one of our open hardware projects. It's a lab kit that we use for a vibration mechanics course, and it was actually published in the Journal of Open Hardware several years ago, the physical kit. And then more recently, about a year ago now, me and another student in the lab, John Antelik, designed this circuit board that can run the whole lab and allow for more quantitative investigations into these oscillating systems. And the way that it works is this is kind of the main board, and it has 3 ports that can connect to accelerometers. It also has a bunch of strobe lights around the outside, which hopefully will show up well on camera. And it has a headphone jack, which it can use as a function generator output. So this is one example of the lab kit. But what I wanted to show you on the screen is we had another undergrad researcher, Aaron, work with us to develop a really wonderful user-friendly web UI that connects over Serial. But unfortunately, that's not going to happen today. So let me get this thing going. Okay. So we got a strobe light. It's doing some strobe things. So I have the function generator sending like a sine wave to this, which is just a speaker. And then that's getting amplified through a little audio amplifier. And then that's driving this, which is the kind of the main forcing part of the system. And then this is just a normal like hex nut on a spring. So it's nice and springy. And if I crank up the amplitude or the volume going to the thing, you can start to see that the nut is now moving relative to this part, which is forcing, which is directly connected to the spring. Sorry, to the speaker. And this really cool thing happens where you can see the nut moving in this oscillating system as if it's in slow motion. And so what's happening here is because we're strobing the light at a slightly detuned frequency from the driving frequency of the speaker, we're aliasing the signal. And we're aliasing it so that we can see it with our eyes at a reduced rate. So this is actually what it looks like to me. I'm seeing this 60 hertz wave in this case, which if I were to, let's say, turn the strobe off, it just looks like a blur. It doesn't really look like much of anything. If I get like a continuous flashlight on there, you can see it really doesn't look like much. It's just kind of this blurry, fast-moving system. But then when the strobe light comes on, all of a sudden you get this cool effect where it's showing as if it's in slow motion. So another thing we can do is right now it's oscillating at 60 hertz and strobing at 61. If instead I strobe at 62 hertz, now we get this detuned aliased signal at half or at double the frequency. So now we're seeing it oscillate at 2 hertz instead of 1 hertz. And I can do that again. I can go up to maybe 63 hertz. So now we get that. We can do lots of other fun things. So if it's strobing at exactly the same frequency as it's oscillating, then we see it as if it's not moving. But then there's a fun trick where we have a slider on the website that sweeps through the phase. And so now, by scrubbing this slider around, I can kind of play the oscillating system backwards and forwards and see exactly what phase it's maybe at the lowest point, where it's at the highest point. I can see this all happen with a lot of detail because I'm scrubbing through the phase. Another fun thing I can do is just do a instantaneous change for what phase the strobe light is strobing at, which looks really uncanny IRL, because it kind of just looks like it moves instantaneously between 2 points. So that's pretty fun. Let's see, another kind of fun thing we can do is strobe at double the frequency +1, so now 120 hertz. So now we're seeing it kind of play both forwards and backwards at the same time. I don't know how well that's showing up, but we get this really weird doubled image effect that kind of makes you feel like you're going crazy. Yeah, so that's some fun things that we can do with this reconfigurable kit. And with the last remaining few minutes, I will show one more similar system. So this is a normal speaker with this 3D printed bath. And the bath screws on to, again, like a 3D printed mandrel sort of thing. And this all can just be printed on an FDM printer. For this kit, we have paper coming out soon, but basically there's an alignment jig that helps you glue it on in place on the speaker, and then you can have different baths and screw them onto the speaker like that. And then when we fill it with water and put something on the surface, we've replicated our big shaker system. And this is specifically kind of comes with a curriculum for high school physics labs where you can see Brownian motion by exciting Faraday waves on the surface. So we have 2 minutes. Maybe I'll pour some water in here and we'll make some waves. That's fun. Okay. So. Kind of see some waves. And as I increase the volume to the speaker, at a certain point, there's something called the Faraday instability, which is when the surface is no longer stable when it's flat. All of a sudden, we get this pattern that is random across the whole surface and is kind of always changing in time. And so this creates a random forcing background for an object placed on the surface. So now if I find something to put on the surface, so for this experiment, these are little 3D printed boat looking things. It's like a tiny bottle cap, 3D printed out of FDM plastic. And if I'm kind of careful, I can place it on the surface like that. And I'll turn the volume back up to get it over the Faraday threshold. And we'll start to see this object move around. And it turns out that because the forcing is random, the motion of this object mimics Brownian motion. And so this is a high school lab that you could do in a physics class and use a camera from like a cell phone, for instance, to film this nice black background with a white circle, track the circle over time, and then when you plot the velocity over time or the position over time, you'll see the same characteristics of random Brownian motion. So another cool open hardware project focused on science education and being able to see some of these cool physics concepts, but at a human scale. And that looks like my time. I'd welcome any questions, or thank you so much for letting me show off our stuff.
Thank you.
Yeah, that was wild. Cool.
That's so cool.
Oh, thanks.
I was
Thanks,
talking
Sid.
to physicists recently because that's the thing I do. And they're saying all these things, and I was like, well, I got to know a guy who works in a fluid physics lab, and it's pretty cool.
I'm just the guy who builds things, but the lab is pretty fun. We do get to play around a lot, which is pretty cool. Very lucky.
And before we ceremoniously toss you off, Smart was wondering, if you put something inside the water, would it stay in place?
If I put something inside the water, like under the water, or I'm curious.
Yeah.
Like,
I think
that's a good question. I want to try it. So I think it depends. So this is like a little boat, so it's buoyant at the surface. But if I sink it, let's see what happens. Well, okay, there's a little air bubble trapped. So now that it's sunk, I think there's just too much friction on the bottom, and so it's just kind of sitting there. But maybe if we got something that was like perfectly neutrally buoyant, I'm not sure what would happen. That would be an interesting thing, and something that I would ask the various PhDs in my lab to think about.
we couldn't possibly just do
Yeah,
it.
I love it. This problem.
Yeah.
Yeah, looks like not much happens, but maybe we're not doing
Thank
it right.
you.
Maybe I missed the question.
We'll talk to you soon.